Hello and welcome to a video of overfitting solutions. So let's start with knowing what is overfitting. Overfitting is when a machine learning model learns specific patterns of the training data and perform bad on unseen data. For example, here in the case of this, as shown in this figure, there are two classes. One are this blue dots and the other is this red dots. So each dot is an instance which belongs to a specific class. The green curve which is separating these two instances to classify them is representing the learned model for this classification. But the issue is it is overfitted. Why? When we gave this data to model to learn, the model learned this specific example, which is shown here in this figure, to classify both the instances in different classes. But when the new data will come, this exact curve won't be able to classify these two instances in accurate classes. But if the learning made by model was this black curve, it has learned the general pattern over here. Few of these instances, for example, blue one is here from the line and the red one is here, because of the nature of a fault in nature of recording of data. There is always noise in data sets, and due to which it is shown a bit distracted from its paths. But the actual underlying reality is the blue class actually belong here. Let's say it is class 1 C1 and the other class actually lies in this area, which is C2. But this green curve is not able to classify the unseen data exactly. And if we talk about how overfitting is diagnosed, so when we see good results on training data, but uh, very bad results on testing data, means there is a huge difference between training data results and testing data results. Overfitting has happened, means our model has gone biased towards the training data and it is not performing well on the testing data. For example, if a model gives 99.9% accuracy on the training data, but when it is tested with the testing data, it only provides 50% accuracy. It means our model has bias towards the training data and not giving the good results on testing data. So, what are the solutions? How we could avoid the overfitting? So, these are the possible options of solutions, and let's discuss them one by one. First is validation set. In machine learning models, we usually have our training data. Let's say here is a portion of data which is training data and our testing data. Which we use to test the learned model. But if our training data is gone overfitted, so model will not perform good on this testing data. So what we do, we make 3 splits of the data instead of 2. We also add a validation set with training process. These two data sets are used in training, and this one as remains as testing set. So how it is used? Let me briefly explain it. When we train our model on this set, for each iteration of training, uh, for after each iteration of training, we test our model on this set, which is validation set. And it also helped to learn the hyperparameters of the objective function. If training data is gone biased toward, if the model is gone biased towards the training data, it will perform bad on validation set. So we adjust the parameters of the model and make it to perform good model on validation set. And it makes our model not going toward the overfitting, because every time we are checking it on validation set. So it will prevent overfitting. The next one is increase the data. Means if we were training a model on a data set, let's say for example it was 1000 instances and it was making overfitting. Increase the data, make it, let's say, 10 times. Take 10,000 instances. But what will happen if we increase the data? As it is an assumption that we increase the data, more variation within the instances of this data set. For example, each instance of the data will be different from each other, or at least a bit different from each other. When it is 1000, there are 1000 variants of the data. But if they are 10,000, it means there is more variety in this data. When the more variation in this data, our model could not go biased towards some specific instances of data, and it remain general towards the whole data set, and it could avoid overfitting. But it is not actually the ideal case, not ideal in every scenario, because we could not have that much data for every problem. So next option could be less parameters. What does it mean? The more trainable parameters in the model, the more chances of fitting the noise. Means if we let me show it by an example. Let's say we have few data sets over here, and we want to draw a polynomial which passes through these points, and we put and we make the degree of the polynomial, let's say 1. Degree is equal to 1. And if a polynomial has degree 1, it could only generate a straight line. So what are the chances? We generate a straight line here, it doesn't capture the actual reality. We generate a straight line here, it even doesn't capture the reality. So what we'll do, we need to increase this degree. Let's say we add +1 here. So what could be the new shape of the curves? They could be like this, like this. It is not even capturing the actual reality. So as we are increasing the degree, it means we are increasing the parameters of the model, because when the degree is 3, we need at least 4 numbers to represent a 3-degree polynomial. For example, let's say x3 plus 9x plus 9x squared 2x plus 3, let's say. So 3-degree polynomial, we at least need 1 here is the coefficient is 1, 2, 3, 4 parameters to present this polynomial. As we are increasing the number of degree, we are increasing the parameters, and with increasing the parameters, we are increasing the power of the model. When the power of the model is increased, uh, it is making it possible the new curve would exactly fit these noisy points, and it is not actually uh, capturing the underlying reality. So uh, parameters should be good enough to capture the underlying reality. Let me Okay. So we do not we should not have so we should not have so much parameters which will lead us towards overfitting. We should have a good number of parameters which actually fit the underlying and capture the underlying reality. The next option is regularization. Uh, every machine learning model have an objective function, uh, which we need to reach for the optimal learning. And if what is regularization? Regularization is we add a term in that function such that it stops the learning process to go towards overfitting. For example, as shown in this figure, this is the objective function of polynomial curve fitting. And polynomial curve fitting, and it is an error. So obviously it is an error, so we want to reduce the error. And here's the objective. We want to find such a vector which reduces the error. So reduce W, to reduce the error, we want such W that gives less error. But it finds somehow a W which gives less error, but it goes towards overfitting. To avoid this overfitting, we need a regularization term added within this objective function. The rest of the function is same, but a new term is added. Overfitting was happening due to big coefficients of W. But what we did, we add a regularization term which contains a W. If the coefficients are higher, a squared number of the coefficient will be added to the term and the error will be increased. So we bound our objective function such that the regularization term is controlling the error. So if it want to give us the good number, means a less error, the coefficient of W should not be increased, and they was the cause of overfitting. And here is a hyperparameter named lambda, which controls the impact of this added term to the error function. Okay. The next option is early stopping. So let's learn what is early stopping. As we talked about the validation set, so let me make a figure for you to understand this. Here is the loss, and here is the time. The intention is, with time, if we go towards higher number of times, the error will be less. It is an intention. but actually it is not happening like this. This curve, let's say, representing the training. But when we add a validation set to verify it every time with each of, let's say these are the iterations, the more time, the more the iterations. So with the time, when we checking it on a validation set at a specific time, the validation set is giving a lowest possible number of loss at a specific time, but it start increasing after that time. So if we keep on learning, our loss is going towards down, but validation set is giving a greater loss. And as we already have learned, the greater the loss with the validation set, it is overfitting. So it is indicating a point after which there will be overfitting. So we stop this learning process at that time. So it is called early stopping. So we stop the learning process at a specific time before it goes towards overfitting. Now let's move to the Jupyter notebook and see some Python code for the solutions of overfitting. As we discussed, there are many solutions to overfitting, but we'll see a couple of examples here how we could control the overfitting. We have already set in an example where we imported the important libraries. We created a data set with some randomness in it, and we split the data in training and testing. We fit the polynomial on the data with numpy function polyfit, and we visualize it here. So as one of the point was, when we increase the power of the model, it goes towards overfitting. Here we put the polynomial degree at 9, and the training data was overfitted. As we can see from the figure, the blue line is training data, and the blue curve is trying to pass through exactly the points, but not covering even a single point of testing data. It means this is a situation of overfitting. Our function is performing, our model is performing good on training set, but it is not performing good on testing data. So we are using the first approach here to overcome the overfit, which was increase the data points. So we changed the data a bit, and we increased the number of data from 20 data points to 100 data points. And again, we split the data into training and testing sets, and let's see what happened when we increase the data. Here is the data plotted, the 100 points, and when we fit using the same power of polynomial, which was 9, the training data was fitted perfectly, and it is also fitting the testing data. As we can see here, the blue line is exactly passing through these yellow dots, these yellow points which were testing data. So we did not, as we can see here, it is polynomial degree 9, and we also use the polynomial degree 9 here. But when the data was less, it was going towards overfitting, and we increase the data and the overfitting is gone. The other one was, we should have less number of parameters to control the overfitting. Less number of parameters means the number of parameters should not exceed a specific number for the specific data. For example, we increase the data, it is 100 points. And even if we increase the power of the model from here, we moved to 12 from 9. We use the polynomial degree 9 first, but we are using polynomial degree 12 here. So we can see here our training curve is exactly fitting the training data, but as soon as it reaches to the testing set, it is deviating from here. Means a model is very powerful, it exactly fitted the training data, but it is again performing bad on testing data because our model was very much powerful, and it should be up to a number of parameters where it suits the both data sets, training and testing data sets. I hope you like the video. Please subscribe our channel, like this video and share this video to your fellows. Hope to see you next time.